try to remember to check in, see if there's others waiting. Okay, well, I'll just say basically good for you all. Like I mentioned in one of my posts, everybody passed. I know you'd all love to ace everything and understand everything, and it doesn't always happen. But from my perspective, I'm glad for you all. I'm happy. I know it's not the same, but I get nervous for you all too. Want you to do well. How's it going? Is it making sense? Whatever. Anyway, let's see. I think still Monday night. I had postponed the last couple assignments till tonight. So if you haven't gotten those done yet, most of you have, but try and get those done. I'll catch up on the second-hand homework. That's me being slow. Took the weekend off mostly, letting people in here. But here we go. We're on to chapter 2. And it's kind of a busy, kind of a full week. I mean, or a full chapter, full section. You've all been real good about showing up. And I just encourage you to keep doing that, and or at least watch the videos. Keep up with the homework. Don't try not to wait till the last minute. So chapter 2 has to do with solving equations, right? Solving equations. Well, we haven't really been dealing with equations yet. Most everything we did in chapter 1 was dealing with expressions, variables plus constants organized together, representing some relationship perhaps. And we simplified those expressions, or we evaluated them by what would we get if we put a number in for that variable. We evaluated the expressions. So, now we're going to step up and say, well, let's take the relationships a step further. And what if that expression is supposed to be equal to some value? What value do we need for the variable in order to make that work, to make it true? Is basically a concept. We're going to solve equations by finding the value for the variable that makes the relationship true. So before we jump deep into that, excuse me, you may recall back in section 1.9, it was called properties. Really all we dealt with there, rather quickly, I can tell from some of you, that was the distributive property. But there were several more things in that section that I would like to touch base with right now. It'll help us understand why we're going to do some of the things that we're going to do. Mathematics is a language. You mostly learn it sort of organically or through experience in the real world, growing up by counting and measuring things out in the real world. But might say the power of mathematics or the complication, it gets there, right, is in the relationships that can be built that actually can be used to predict things that we don't directly observe, something like that, algebra in particular, dealing with equations. And if I have this equation, I can actually make a graph that shows what's going to happen if I go down the road this far. So that's kind of where we're going, right? Long story. So in section 1.9, we did talk about distributive property. We'll continue to see that even today in some of our examples. But our language really is built on a couple of basic assumptions that you'll just say, oh, really, I understand that, take that for granted. But kind of mathematicians at some point sit down and say, okay, we're going to claim this is true, and from there we can build everything else we do. Simplifying, of course. First of all, I want to talk about a property that you may have heard of, kind of threw out a couple times, called commutative property. And sort of the root of that word, I hope you can read my writing there, is commute. If you commute, you travel, you change positions or locations. And so we have kind of been using the commutative property a little bit without talking about it a whole lot. But you'll see, for instance, this applies to both addition and multiplication. Okay, the commutative property basically says you can change the position of the numbers you're adding, and it doesn't change the result. It almost makes sense. Oh, now order of operations tells us, oh, we have to take these in order, left to right. Now we're going a little farther and saying we got recognize this relationship that says almost you can break this rule. We can move some things around if it fits the situation. Commutative says the order doesn't matter if I'm just adding, right? 2 plus 3 is 5, plus 4 is 9, but I can do 3 plus 4 plus 2, and I'm going to get that same answer, right? I can move them around. The same is true for multiplication, right? If I multiply those 3 numbers in a row, you know, PEMDAS would have said, you know, 3 times 4 first, and then times the 5, and get 60, but I can move things around if for some reason I want to, and I get the same result. My multiplication doctrine comes through. Okay, that doesn't seem like a big deal, perhaps, but notice it doesn't apply to subtraction, right? 2 minus 3 is not the same as 3 minus 2. We understand that. Or 6 divided by 12 is not the same as 12 divided by 6. It doesn't work for subtraction or division. They get different results. Let somebody in here. Come in. But, all right, so what about something that looks like, let's make sure I get this right. 7 minus 2 plus 3. Well, Order of Operations says, oh, we've got a mix of add and subtract. So we have to take them in a row. We have to take them in order. 7 minus 2 is a 5, and then plus another 3 would get us to 8. Like Steve, right? What you have to avoid is not saying, oh, that's a 5. 7 minus 5 is 2, right? Well, recall that we can always think of subtraction as adding negatives, adding the opposite. Some of you even prefer to write some of your answers like this. Everybody okay with that? All right? So subtracting a 2 is really the same as adding a negative. Well, now I've just made it an addition problem. As long as I keep this negative sign with the 2, I can move these pieces around. Or 7 plus 3 minus 2 is going to give me the same answer. This negative, think of minus 2 is like adding a negative, or the negative, as long as you keep the negative sign connected to the 2, you can move the piece around. I'm going to get the same answer. So when we have, whoops, my board, stable, get stable. You know, if I've got a like terms kind of problem like this, and I want to combine like terms, already we're kind of saying, oh, I can put I'm not taking them in order. I can put these x's and those x's together, and I can put this -5 and this 7 together, and I've simplified. I'm kind of commuting, moving things around, putting things next to each other that I want to be next to each other to make it easier. My point here is, as long as I kind of keep that negative sign with the number it's connected to, I can move that like a unit. I can move it around. I can commute it also. Even so, it looks like it's breaking the order of operations rules, but it's not. So, okay, sure, Steve, we'll see where it works. See when it comes in handy. Like I said, we've kind of already been doing that with these simplification problems. So I just wanted to address that, being able to talk about commutative. Yeah, it's okay to do that. Remember, you can move the order. That's one property touch base with. All right, here's a couple you go, duh, right? Identity element or number. There are numbers that are, we call them the identities because they don't change what they're connected to. For addition, what number can you add to anything and it doesn't change it? It's the 0. To add 0 to anything, we agree. So this is like one of those building blocks. We have to say that 0 doesn't change anything. We can add 0 to anything and we just get the end of things. So eventually we just ignore the 0. That's kind of what we're doing. You see, maybe I'll use this idea later. Multiplication, right? What can I multiply any number by and it doesn't change it? For multiplication, that identity element is a 1. 1 times anything is just the anything. Okay? I bet you're all good with that. I go, oh, all right, so 0 is the identity element for addition. 1 is the identity element for multiplication. All right, well, what does that mean? Well, we're going to deal with equations where we have numbers added and subtracted. We want to kind of cancel them out. So the next idea is inverses. Every number has an additive inverse. And a multiplicative, I like that word, multiplicative inverse. The opposite, right? Inverse is opposites. It does the opposite thing. Well, for additive inverses, they add to 0. So what number do I add to 5 to get to 0? It's additive inverse, or the opposite of 5, a negative 5. We add them together to get to a 0. And we're going to see in our equations, we'll use that to kind of cancel out a number. So we get to a 0, and then we can say it's just the thing we wanted. So additive inverses, just plus or minus the same value, let's say. Absolute value, the same absolute value. Multiplicative inverses multiply to 1. Right? So, what can I multiply 3 by to turn it into 1? Its multiplicative inverse is the reciprocal. Reciprocal. Right? 3 times 1/3 gets me to 1. So every number has a multiplicative inverse. It's the reciprocal of that number. And if it was negative, it would still be negative. Negative times negative would get us that positive. So these are a couple of properties that we're going to use over and over in our solving. Just setting you up. Like, okay, I see that. Now, what do we do with it? So I just wanted to touch base on those because we we skipped them in chapter 1. But here they're really going to apply. Now we're going to use them. So here I go. I'm letting go all this, and we're going to jump into chapter 2. Solving equations. 2.1. We use addition and subtraction. Well, the first thing though we're going to do is verify. Is a certain value a solution? I already said it, but let's say it again. A solution to an equation is going to be a value for the variable that makes it true. Value that makes it true. Okay, we're looking for solutions. So here's a basic equation shape. Here's an expression, 3 more than twice a number. I know your favorite, right? 3 more than twice a number. Well, here we're going to build these relationships that are saying 3 more than twice a number is 7. And so we're going to be looking for the value for x that's going to make these two things equal. An equation claims that 2 expressions are equal to each other. And here we're saying this expression is equal to this single constant value. We're going to get into things that look like messy stuff on both sides eventually. All right. So to verify is, well, let's see, is 2 a solution? If x is a 2, does it make this true? So this is like you did last section, evaluate. Plug in the 2 for x. 2 times 2. Oh yeah, that makes it true. 7 equals 7, it's true. So yes, 2 is a solution. We have verified that 2 is a solution by plugging it in and boiling it down to this true statement. If I put in, is 5 a solution? Right, well, can I test the 5? Basically, yeah, we're testing, right? 2 times 5 plus 3, well, 10 plus 3, that's not going to equal 7. No, 5 is not a solution. First step, verify. That's, you know, got to be able to do that. It's like checking your work when we get to the end of these problems. You can always go back and plug it in, see if it really works. Okay, so that's our verifying process. Plug it in and see what you get. Okay. Our first type, solving by adding or subtracting. Here's the first simple form of equations we're going to run into. We're trying to boil these things all down to the same x equals what? What is fill in the blank? We want to get down to x equals this number. And then we know what makes it true. That's the solution, right? Well, here we're going to use those additive inverses to cancel out that 3 so that we can get the x all alone. We're going to, in a sense, do the opposite operation of adding 3. We're going to subtract 3. Important concept here, though, an equation. It's like a balance, a teeter-totter. You can't see that, it's too small, right? But this is my big fulcrum here. There's my equal sign, right? The equal sign is like the balance point. Whatever's on the left, is supposed to equal what's on the right. And if you change one side, you've got to change the other side to keep it balanced or equal. That's the primary concept. Whatever you do to one side, you got to do to the completely other side also, over and over. Good, somebody else come. So what I want to do is get this to be basically, if I can get it to x plus 0 equals something, my property before my identity means I've just canceled the 0. We don't have to write this usually, I'm just showing right now. So I'm going to add the inverse, and I'll write it a couple different ways. And then you can choose the way you like the best, okay? So here, I added to both sides, which makes it legal, I added the opposite of 3. I added the inverse of 3 to both sides. Now it's still balanced. If I put those 3 together, they're inverses, I get the 0. Over here, 7 plus a negative 3 is a 4, and that means I know x equals 4. I added the opposite. Now, we're going to just shortcut and say minus 3, right? I don't have to write it as adding a negative. I can just say plus 3 minus 3. Hope you're okay with that. Just a different notation system. I'm going to show you one more way you might like to write it for yourself, okay? I'm going to leave the original, I'm going to erase this. If you know, you might say what you want to do. Oh, I want to cancel out this 3 is kind of what we're doing. I want to subtract 3 from both sides. Just a lot of students like to use kind of the arithmetic format, or let's just do this, right? 3 minus 3. So all that's left is this. I'll be okay with you just, in your notes or scratch work, showing what you're doing vertically like that for add or subtract. It works. Formally, mathematicians, we like to use that previous format I used where you actually write everything horizontally, one step at a time. It's like writing a good paragraph and punctuation in your sentences and stuff like that. This is the gist of using the inverses, additive inverses, to solve this equation. I can plug it back in, right? 4 plus 3, yep, that equals 7. Just do it again. X plus 6 equals 11. What must x be? These seem easy right now, that's great, okay? I want to cancel out the 6. I want to get the x all alone, right? I want to undo this adding of an extra 6. So I'm going to subtract an extra 6. And you don't need to write this line, but that really gets us to x equals 5. Notice I even just skipped the 0 step. Right? I know I use the opposite. That property says basically I can ignore that 0 now. So I added the inverse, or I subtracted that number from both sides. Here's one where I'm subtracting something from my unknown variable. What does this number have to be so that I can subtract 5 and end up with an 11? I'm going to do the opposite of subtracting 5. I'm going to add 5 to both sides to get this 5 to go away over here. I'm going to write it out again. Right? These two cancel each other out, and I can ignore that step really. You don't have to show me that step. I'm just presenting it over and over here to get you used to the idea. All right, and notice I did just use that sort of vertical format there also. Otherwise, I might have written x minus 5 plus 5 equals 11 plus 5. Straight row. Some of you in a lab class, some of those lab teachers might want it one way more than another. This is one way that I find students find comfortable with. Okay, it's vertical format. Adding and subtracting. How about fractions? Yeah, they're not going to go away. We won't. When presenting basic ideas, we probably will avoid the fractions to start, but then they'll show up eventually in problems. Well, my x value, my unknown, has an extra half added to it, so I want to cancel out that, do the opposite of adding. Think of the opposite operation. Opposite of adding is subtracting. So I'm going to subtract. Fractions kind of work a little bit better in this horizontal format, because over here I'm going to have to do what? Get common denominator before I can do it. Right? So here I've subtracted. I've canceled out the halves, excuse me. Now I just need to do the work over here. Everybody okay with 4 over 4 gets me the common denominator, right? And now I just perform that operation. I do have a common denominator. I will end up with a quantity of eighths. 3 minus 4 means I have a -1. Don't lose that negative sign. -1/8 is the number that would have made that all true to begin with. Adding and subtracting. Thumbing through my notes here. Yeah, just making sure we keep track of everything. Let's do another one of those, okay? And all right. What operation, what am I going to do to get that x alone? Somebody want to pipe up and how do
Plus 4/5.
I'm sure you said it. Say again.
Plus 4/5.
Plus 4/5. Good. Yeah. The opposite of subtracting, I'm going to add it. I'm going to write it out horizontally because it works better for fractions over here. Got to do the same thing to both sides. Fifths. All right. These go away. What do I have to do over here?
Add them together.
Add them together. I need to get the common denominator. 15 works for both of them. So 3 over 3 times 3 times 3. And now I can add them a bunch of 15ths. And as always, when you add or subtract, you got to look and say, oh, can I reduce? No, 19's a watch my time. Okay. So yes, add and subtract. You might see a fraction, occasionally a fraction or a decimal. Add or subtract the fraction values. Sometimes we have to do a little work before we're ready to do that. That is simplify a bit. How about, say, in this first section, they're all going to, whoops, -7, all right. This first section, they're all going to sort of boil down to 1x or 1y. Oh, I mixed my variables. Let's make them both x's. The paper said y, but I started writing x's, okay? Make sure we get the same variable, otherwise we don't know what to do yet. So I have a bunch of pieces here that are supposed to equal a 4. Look for like terms. Simplify. All right, simplify the like terms. Put them together if you can. This is where that commutative idea is being applied, right? I've got some x's. Are there any more x's I can just mentally at least put next to each other and combine? 8x plus a -7, right? Or 8x minus 7x means I have 1x left. -4 minus 7 more, -11. There, I've combined the like terms. I've simplified before I'm ready to do this add or subtract process that we're talking about right now. So now it's less
10
messy.
plus 11
Add 11, yeah.
on both sides.
Good, good. I know I try not to go too fast, but then I know sometimes I just go on. So 15 is the number that would have worked in all those x positions there to make that original relationship, whatever it was, true. So simplifying a little bit before we do what we want to do. Or how about whoops, okay.
Sorry, I didn't get to write down the answer to the last one, just to make sure I was on the right track. That was -7 for the last one.
It's 15 plus 15.
15?
Yeah, x
Is it
equals
15? 11 plus 4.
Oh, because we're adding the 11. Okay, thank you.
Good, good. See, right? You got to realize what's the sign or the operation you're doing on both sides. Good. Here's one that we're still looking to simplify before we can combine and then sort of isolate the x. Here, though, to simplify, I need to distribute. It means 5 times both of those values. Just 5 times what's the parenthesis it's multiplying. I saw somebody try on the test try to do, well, then 5 times everything that came after the parenthesis. Now that's like separate pieces over here. Right? Just right here, I'm going to get 5x minus 15 minus 4x is -10. Now I need to do that sort of combine like terms thing. I've got some x's, 5 x's minus those 4 x's means I still have 1x. That's what I'm getting at. In 2.1, it's always going to boil down to just 1x. Because then I just have to add or subtract whatever this is. Opposite of the subtract is to add the 15. Good. And that cancels out, gives me the 0, so I can just say the x is 5. Always doing the same thing to both sides, keep it balanced. And on to another, here we go. Make myself more room over here, just in case. Yep, let's do this one. Not too bad yet. Just now we have to simplify as much as we can before we can get down to that point we're ready to do that last step. How do we get down to plain X? Distribute here. Notice here's my equal sign, right? I've got stuff to distribute. And I have some stuff to distribute on that side.
Can I work through the problem?
Pardon?
Can I do the problem?
Okay. What do I got? What do I have next?
8x
Yeah.
minus 12
Very good. Yep. 4.
minus 7x equals 6x minus 12
Yes.
minus 6x plus 6.
Plus 6. Good. Right. Minus this and minus minus. Good. Fortunately, we need to keep practicing distributing, don't we? Good. Good. Very good. Now I have simplifying to do on both sides. All right. 8x is minus 7x. Did you want to keep going or shall I? Go ahead.
If I don't care, I can keep going.
X minus 12 over here. Is that all right?
Yeah.
On this side, I have plus 6x. Oh, and minus 6x. Yeah, we're not ready to have x on both sides. And what? Negative 6?
Yeah.
Add 12?
Yep.
X equals 6.
X.
So the point of that one was having to do some work on both sides to simplify. Ugh. Here I go. All right. Word problems aren't going away. Now we're going to try to take that word problem expression kind of problem you dealt with in the first chapter and say that expression is now equal to something. We have to write the equation ourselves and then solve it. How about 10 more than x is equal to, it doesn't matter much, 41, squeeze it in over here, okay? 10 more than x is equal to 41. All right, what's our technique here? Look for the equal sign expression. Is equal to. Is equal to. That, in our translation, that's going to be the equal sign. Is equal to. That's equals. Then we got stuff on the left, then we got stuff on the right of that equal sign. 41, it's all alone over here. 10 more than x. X plus 10 or 10 plus x. Addition, it doesn't matter. All right. There's our translation from the sentence to an equation. Solve. I didn't say talk it through. Is that okay, the solving? Let me know if I lost you. All right. Here goes. I'm listening. 3 less than a number is 4. All right, same kind of situation. We're going to translate this into an equation. Look for the part of this sentence that represents the equal sign. And this is sort of the simpler version of the last one. Instead of just saying, instead of really writing it all out, is equal to is. Is going to stand for the equal sign. Is. This stuff is 4. Okay, eventually we condense. I purposely did this for a subtraction. It's unfortunate a couple of you had trouble. I've seen it before. For some reason, you get the two parts to this subtraction expression that reversed. 3 less than a number. It's this many less than, this is the starting amount, right? A number. Now, again, here I sort of changed language. It didn't say X, but we've done this before, right? There's a number, there's the expression that stands for our variable, a number, the unknown. But I want 3 less than that. X minus 3, not 3 minus X. I know 3 was first in the sentence, but this amount less than some given or unknown there. Now, so there's my translation. Add the 3. That's the challenge, of course, always, I understand, for the word problems or to translate it. Right? Strictly, we would say maybe that was a word problem, and then we get to things that we call more like applications. They really are what you probably call word problems in school, where it's a real attempt at a semi-real world situation rather than abstract stuff here. Okay, here we go.
I have a question.
Yep.
So like the ones that not the word problems, the ones before that,
Okay.
they are on the homework. Can I give you an example? And I'm not confused, but want to know how to solve it, I guess. If that makes sense.
You mean with the parentheses?
No, not the parentheses one though.
Oh.
So it's like 7x minus 9 equals the parentheses all the way at the end too. So how do you find, I understand you do the parentheses and then you do the, but what if the, whatever I said was x cancels out on both sides?
Oh, okay. So you are getting ahead of us. I'm gonna, if you want to talk to me about it later, fine, but
Okay, sounds good.
yeah. I'm being methodical here. And in fact, we haven't, what if I've got 7x equals a number? That we haven't talked about that. Everything right now so far is just x equals plus or minus. All right, so 7(2) is, what if we got more than one x to deal with? Trying to get there today.
Sorry.
No, it's all right. Okay, here we go. So let's see. Randy, whatever you want. Hey. Oh, make a nice round number. 28,000 for his car. This was $800 less than sticker price. Right, sticker price. What was the sticker price? Getting sloppy, sorry. What are we looking for? What are we looking for? We're looking for the sticker price. It's unknown, right? 800 less than the sticker. There's an expression. Sticker is the unknown, right? X or S or whatever. This was, that's like past tense of is, right? This is 800 less than the sticker. I wrote it as 2 sentences, but there's still a sort of equal sign expression here or word, right? Is or was. This was equal to 800 less than the sticker. All right, so 28,000 is 800 less than the sticker. And is 800 less than the sticker. If X is my sticker, 800 less than the sticker. I didn't notice, it was okay. I put the X's on that side. I could have.
So I got there. I ended up getting that right answer, but I just flip-flopped it. I did is that still right technically?
I was just starting to say, it doesn't matter if you did this, right?
So it won't be wrong if we end up writing our word problems like that. Okay, thank you, because word problems I've always had a trouble with.
some number equals x instead of x equals some number. And it doesn't matter which side of the teeter-totter you're on. Okay, I'm going to add 800. And so 28,800 is x. If you were doing this in a written test in the classroom, we would now expect you to write a sentence answer. The sticker price is, or was, whatever, 28,800 dollars, units. Put your units on there. Complete sentence answer if the problem is framed in a sentence context. Consider a full sentence answer, all right? Mom doesn't get picky like that, but I got to talk about it, right? I want to change gears and talk about our next technique. It's going to, we'll keep coming back to problems like this, where we're going to try to use this technique, whatever technique we're practicing, with application or a word problem also. Little by little. 2.1 was about solving by adding and subtracting. 2.2, we're going to solve by multiplying and dividing. Multiply and divide to find our solution. All right. Again, I want x, 1x. This problem starts out by saying 3 of this unknown value is equal to a 6. What's just one of those values equal to? What I want to boil this down to is that identity situation again, where I'm saying one of these x's equals something, right? Get to the 1. That's why I presented those properties. I need to use the inverse of 3. Cancel out the 3. The inverse is its reciprocal. I'll show you a couple of ways it's okay to think of this. So if I multiply both sides by the reciprocal of 3, 1/3, everybody okay with that? I'm doing this specifically, I chose 1/3 because it's the number that's going to cancel the 3 or turn it into a 1. It's inverse, it's multiplicative inverse. So those, in a sense, cancel each other. I'm down to 1x equals 2. And this is that step where you don't really have to show me, but just explaining how we're using that identity concept. All right, so I got down to x was equal to 2. Most of us now understand that multiplying by a fraction is the same as dividing by that number, right? It's okay. Now, preferably you write your problem and then you show any steps at the next step. What do I want to do? I'm going to divide both sides. Do the opposite of multiplying by 3. What's the opposite of multiplying? Dividing. Dividing by 3 is the same as multiplying by that fraction, right? See how that just becomes the denominator over here? So yes, just like I lined it up vertically, you can do the multiply, undo multiplication with division this way. So I get that x equals 2. Cancel out what's being multiplied, right? Here I have 4 of my unknown values equals 20. 4 pounds equals $20. What's 1 pound? You can just make it up something, right? Well, how do I undo multiply by 4? Multiply by 1/4 or divide by 4. Make sure you do whatever you're doing to both sides. That makes that a 1. You're multiplying through the opposite, divide. Okay. All right. This is saying if I divide my unknown by 7, or 1/7 of my unknown, if I divide it by 7, I get to 3. Well, what's the whole thing, right? I want to get to 1x. What's the opposite of dividing by 7? Multiply by the 7. So I'm going to take both sides and multiply by the 7. I'm trying to show my original, and here's what I'm doing to both sides. Those cancel, got me to 1x, that's my goal there, and 21. I divide 21 by 7, yep, I get to 3. We're getting close to, close to everything in 2.2, not quite. So we'll definitely, do more of this tomorrow and continue on where we just start mixing the add and subtract and the multiply to divide together. Kind of putting these different techniques together as the expressions or equations become more complicated. Let me put another one up here though, like this. Again, we're kind of thinking opposite operation. All right, here you can say, am I dividing or multiplying or both? Oh yeah, I could say I'm both, multiplying by 2 and dividing by 3, or I'm multiplying by the fraction. Now you might think, oh, to undo that, let's divide by that fraction. But we don't divide by fractions. How do we undo that? How do we divide by fractions? Multiply by the reciprocal. Its inverse is still the reciprocal. I'm going to multiply by the reciprocal, the inverse. See, if I multiply those together, it gets 1, right? But I got to do that over here. Make sure I choose the reciprocal, Steve, and not the original. So there's the reciprocal. Reciprocal, yeah. I'm multiplying by the reciprocal of the fraction. That gets it to go away. Here, do I have any simplifying? I might say, oh, that's, cancel some 2's. All right, that, and call that a 12. 2/3 of 12 is 8. We could go back and check. And one more of those. Okay, here it goes. Same idea. Here my variable is being multiplied by this fraction, and it happens to be a negative fraction. Negative 5/8 of x, of always means multiply, right, is equal to, or is 15. What's 1x? Plain positive, 1x. The reciprocal is going to be the inverse. Said it backwards. The inverse is the reciprocal, right? But it's still got to be negative, so we get negative times negative is positive 1. So I'm going to multiply by the reciprocal of that. And because I'm putting all these fractions together, I'm putting in parentheses. Here's my original part. 15 times negative 8 fifths, Steve. Here's my reciprocal, right? A reciprocal of the original. If it's negative, the reciprocal is still negative. These all cancel each other out, and so I get plain old x. Here, I needed those parentheses so it doesn't look like a subtraction problem. Maybe you like putting the 1 under there, because now I can say, oh yeah, divide this by 5, divide this by 5. Don't lose your negative, negative 24 is the number I could have put in for x to begin with. All right, we made a good start here. We did get through most of 2.1 and 2.2, and we'll try to keep going kind of at this pace here this week. We're really just going to build up more and more complicated, that is more simplifying, kind of have to do before we finally use our add and subtract or multiply and divide. At some point, we're going to use the sum of both to finally get down to this. Okay, I don't mind you sending me questions. I'd rather do that in the forum, okay? If you, or a message, and I'll send you, if you're ahead is what I'm getting at, whoever that was. I'll send you answers that way rather than take our time right here, okay? With that, I'll let you go, let me go, and we'll pick it up again tomorrow, okay?
I have time. I have one question.
Okay, one question. It's my Monday. I always have somewhere to go as long as it's not
Do
too
you?
long.
Okay.
As long as it's not too big.
It's not
All
too
right,
big.
folks, so we'll see you later. If you'd like to sign out, we're technically done.
Thank you.
Okay, yes, you're welcome. All right, Gillian, what do you got?
So I'm ahead, so I just want to reconfirm how to do this one.
All right.
I've already explained, I've already done all the work, I just don't know how to finish it, I guess.
I know, I see several of you are through most of this section, this chapter already. That's great. It's like, oh,
Yeah.
not too hard to begin with, something like that. Good. Go
No,
ahead.
in 1.9, 1.10, and geometry are due all today?
Yes,
Correct?
yes. I was really kind of hoping you'd have most of it done before the test anyway, but yes, due tonight.
Fine.
Okay.
So the question is 18x minus 51.
Minus 51.
Yes. Equals 9, just 9, parentheses, 4x plus 5, end parentheses, minus 6, start of parentheses, 3x minus 10.
Okay, so you really are getting into the end of 2.4 kind of fun here, I think, right?
Yeah.
Yes. And this has to do, I can see where it's going, with those classifications. 3 different classifications. What kind?
I did the half of that over there.
Yeah,
I couldn't figure out how to do that half.
there's nothing to do over here, right?
Yeah.
Correct. So this
But
is,
don't we have to get x by itself?
you try to. I mean, I know what's going to happen. I kind of did a little quick mental math. I see something weird is going to happen. Here I got
18x plus 105. It equals 18x. Okay.
what's that, 45?
Yeah.
And minus 18x.
Minus 18x plus 60.
So, whoops, I lost my x. So still
So
nothing to do here. I'll keep working here so we get to the point. Combine the x's means I have 18 x's here. And this, oops, and that's plus 105.
Yep.
Now at this point, you'll see this is what we do in 3.4 probably. You've got x's on both sides and constants on both sides. The technique in general is to try to pick one side, get all the x's on one side, and get all the numbers on the other side. Okay? Adding and subtracting the term. Add or subtract the term. Well, let's see, I'm gonna move all the x's left. I'm gonna subtract those 18 x's. This is definitely ahead of where we were today. All right.
but doesn't it cancel both of them out?
Well, that's what you're asking me about. Yep. That's why I'm saying you gotta read the instructions or wait for me or go back to your text or look at some videos, but these are about the classification types, weird ones. All right. This got me down to no more x's.
So then
I could even stop right here, but I could try to add the 51 to both sides. Right? If I added the 51 to both sides, I got to, that's not true. That's false.
So that would be the correct answer, correct?
So far, so good. Yes, it's the correct answer.
That makes sense.
What this is saying is the x's are gone and it's always false. No matter what number you would have chosen for x, it would not work. There is no solution to this problem. There's no number that I could have put in for x that would have made it true. There's no solution to this. This negative kind of answer, right? That is negative connotation is the word of contradiction. This is what you're looking for. I know it's like the last mom problem in 2.4, I think, right? Contradiction. That's what this special type is. It's called a contradiction. There is no answer. There's no way to get any number to work. A similar kind of problem, all right? A similar kind of problem would have been one that say you subtracted the x's and they're gone again, but I got down to say 25 equals 25. or 0 equals 0. It's always true. And it has no variables that it's dependent on. It's always true. Any number for x that I started with would have made this work out. Any number works. So this one has an infinite number of solutions, and it's called an identity. An identity equation. Now, I used identity as that added the 0. I used identity as the 0 and the 1 as an element, as a number, but this is an identity equation. This side was identical to that side to begin with.
Okay.
So these are the two weird ones. Most everything that we work with, 95% of all the equations, come up with that one answer. That is the one condition that makes it true. That's the conditional equation. Most of everything we work with are conditional equations. There's one condition that makes it true. These are the weird kinds. No solution because it's false and no variables. An infinite solution because it's true and no variables. Okay?
Okay, that
We'll
makes
get
more
more
sense.
of that. I'll have to present it all again in class, tomorrow probably. We'll hopefully get there tomorrow. Okay? All right.
Thank you.
See you, Hunter, and we'll see you tomorrow then. Right?
One thing.
Oh, you got one too. Okay, Hunter, go for it.
No, it's not really a question. I was just wanting to say I was sorry for missing Wednesday. I was dealing with the whole snow thing and the power went out mid-class, and yeah, it was.
Oh yeah, same with
spectacular.
me. I lost work at here too.
Oh, and that was probably our distributing day, right? Yeah. Well,
yes.
anyway,
No, it was review. It was a review day.
it was review. Okay. Well, that's the nice thing about recordings. And as I mentioned to somebody, at least, I don't take attendance. I appreciate you telling me when, gee, why'd they leave? I don't take attendance after that first week when I'm required to. So, it's up to you guys to be responsible and do what you need to do. But I understand, yes, all throughout the valley, there were issues that day with power outages, even on campus.
I did send you an email. I wasn't sure if you did or did not get it.
I'm sorry if I didn't reply. I was probably getting a lot of that kind of stuff. I think that's why I tried to post a message in the forum saying.
Yeah, I did see the message that later that day when the power did come back.
Yeah. Okay.
Alrighty.
Thank you.
All right. Good work, folks. Then I'll see you tomorrow. Okay.
Take care.
Bye.
Okay. Bye.